Hello, thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, and we're here to talk astronomy and space science. And on this episode, we are going to look at a study into Jupiter's role in shaping our solar system. What shape is that? It's rhomboid. No, we don't know. We're also going to look at a white dwarf star that's chowing down on a planetesimal. Sounds appetizing. Observing a rapidly developing ring system, and it's not far away. And if we've got time, an exoplanet that, in inverted commas, may be a life candidate. That's all coming up on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And it's good to have Jonti Horner back with us again, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonti.
Good evening. How are you going?
I am well. Good to see you.
Oh, it's good to be back, although I'm admittedly a bit of a zombie. So I'll warn everybody, I've had less sleep than I should have done in the last couple of days because of the weather. Oh. We had some weather happen on Sunday, which led to the power here being knocked out for 24 hours during a mini heat wave. So I didn't get much sleep then. And then this morning, I've got a colleague from Japan visiting. So I had to pick him, his wife, and their two lovely daughters up from Brisbane Airport. So I've had 6 hours of driving today off the back of 2 nights of not much sleep. So if I seem less coherent than normal, and I appreciate I'm normally not that coherent to begin with, you know why.
Of course, yes, we've all been there. We've had dreadful weather here too, but it hasn't been the extreme heat. It's been the extreme wind. I got woken up last night at about 1 a.m. by the fly screens rattling. It was so windy.
Yes.
They were just shuddering, and I thought, I can't live with this. So I went outside. It was freezing cold. It's supposed to be late spring here. And I just jammed some wood chips into the. I just went off to the garden and grabbed some mulch and shoved it in the wind in the fly screens to stop them rattling. It worked. I've done it better during the day, but it's just been ridiculous.
I know your pain. I mean, having said that we had heat wave conditions and couldn't sleep because of the heat, I'm happy to confess that I've had the wood stove on today because having had 36, 38 degrees, so that's around 100 for our American friends. Last few days, today has been a toasty kind of 15 degrees, and we've got a rain event happening. So we've had everything in the last week. We've had kind of almost tornadic storms. We've had hailstones the size of your fists. We've had 100-kilometre-an-hour gusts, and now we've got rain and cold that makes me feel like I'm back in the UK. So yeah, all happening, and this is why Australia is an interesting place to live, even to the extent that with the thunderstorms we had, got an email through yesterday that our wonderful observatory, Queensland's only professional astronomical observatory at Mount Kent, was closed yesterday. We weren't allowed to go there because there was a bushfire within 10 kilometres of it that had been sparked by the lightning from the storms and fanned by the heat wave in a place that got lightning but no rain. So It's all happening here.
Yes, dry storms are not uncommon where I am. We do get quite a few storms every year with lightning and thunder and nothing else. And they're very well known for sparking bushfires.
Yeah. So while we're on the diversion of the weather, actually, I'll apologise for Maya, the dog chirping in the background, but my partner's just got home. But we're also sitting here with an incredibly heartbreaking and record-breaking storm in the Caribbean. Yes, I know. She's just come home. Thank you for going in with the podcast. Happy dog.
Gosh.
But yeah, there's borderline record-breaking storm in the Caribbean, which is going to be a Category 5 hurricane hitting Jamaica and doing a hell of a lot of damage. And it's one of these that, from a scientist's point of view, fascinating watching it, looking at the radar footage and all the satellite footage. And on one hand, you've got this thing of incredible, exceptional beauty, and on the other hand, the devastation it's going to cause. So
I saw
the people in the firing line for that.
Yeah, I saw the satellite images this afternoon. It is enormous.
Yeah. So you look at the false colour one with the colour of the clouds, which is an indication of the severity of the storm and the shape. And it's the kind of thing that you only see with the strongest storms we've ever seen, typically in the Pacific. So for this thing to not only be happening in the Atlantic, which is less common, but to be, crosshairs on Jamaica, which has had a bit of a charmed life with storms thanks to the high mountains. They tend to bounce and go around a bit. This one looks like it's not so much going to bounce as splat. So
Yeah, when we were in Panama earlier this year, we did the Panama Canal, and they were saying that they never get hurricanes, ever.
Too equatorial, is my
mm.
understanding. You need to be far enough away from the equator to get enough spin, so it's very rare that you get storms getting right up to the equator because Coriolis force and things like that.
Yeah, it's interesting, isn't it? Very interesting. Okay, we better get on with what we came here to get on with, and we're going to start with a study that's been released into Jupiter's role in shaping the solar system. Now, I do recall Fred mentioning that Jupiter, if Jupiter didn't exist, we wouldn't. And this study basically adds a lot of fuel to that claim.
It does. Now, where Fred and other people talk about if Jupiter didn't exist, then we probably wouldn't, ties into something that's a pretty big myth in science communication and still in science papers and stuff, which is the idea of Jupiter shielding us from impacts. And my most favourite piece of research I ever did in my career is proving that to be a lot of cobblers. And it's actually a lot more complicated. Jupiter throws things at us as well as protecting us. So I've always got a bit of an eye on any study that says, hey guys, if Jupiter wasn't there, neither would we. But this is a really interesting one that looks at an entirely different aspect of Jupiter, which is the role that Jupiter played on the formation and evolution of the early solar system, or the formation of the planets. And I've actually been teaching planet formation this week to my undergrad students. I've just, prior to recording this, had a 2-hour tutorial with them where I've been talking about planet formation and brought this story up, because it really highlights the fact that when we often see in documentaries and the stuff we get taught at school, we get the impression that everything's solved, that we know the answers, that we know full well how the planet's formed in microscopic detail and we've got everything figured out. And the reality is that we haven't. We have a really good broad picture, and we're getting better and better at understanding the processes that went on. But there's still a lot to learn. And part of that is that while we've known the solar system since the year dot, we've only known other planetary systems for the last 30 years. And in reality, we're still learning an awful lot about the planetary systems we find elsewhere. And learning about them's cool and all, but it also gives us insights that help us better understand our planetary system and how it formed. And that ties into this, because the more we study those other planetary systems, the more we're getting observations of really beautiful things like planetary systems that are in formation, where you've got a protoplanetary disk, and we're getting these gorgeous images from things like the ALMA array, the Atacama Large Millimeter Array, that shows disks of planet-forming material around stars with gaps in them, and ripples in them, and bands in them, and all these beautiful structures. And some of these have been previous astronomy picture of the days. Where this ties into the solar system is if you imagine that kind of stereotypical image of a protoplanetary disk, a disk of gas and dust around a young star like the sun, where material is feeding in through that disk to the star. So while the gas and dust is orbiting the star, there is this kind of sense of inward motion where the star's kind of numbing at the inner edge of the disk, material's falling in and more material from outside's flowing in to replace it.
Yeah.
And some of the models of the formation of the solar system struggle to make the terrestrial planets as a result of that, because the material in the inner solar system is destined to fall onto the star. And how do you stop that happening to let that material hang around to actually form into planets? Now, it's been pretty well established for a long time that the first planet that formed in the solar system and got to a good size was Jupiter. And there's good reasons for that. It formed far enough away from the sun that the temperature was cold enough that the disk was rich in ice, which at the distance the Earth is from the sun, all that ice would be gas. When you're forming solid objects, you need solid objects to feed from. And so when you've got a lot of ice, you've got a lot more solids, so things grow quicker. There's a lot more to eat. And it's only when you get to about 10 or 12 times the mass of the Earth that you're massive enough to effectively start gobbling up the gas as well. So Jupiter formed beyond this point called the snow line, where there's a lot more solid material. It got to grow really quickly. It grew quicker than things further out, because the further out you go, the slower things happen. So Jupiter was very much in the sweet spot, grew really quickly, and eventually got big enough that it started clearing the gas and the dust. It could gather the gas as well. And it opened up a gap in the disk. And that's very analogous to what we're seeing with these beautiful images from ALMA, places like this. So the team of researchers behind this work have run some really in-depth computer modeling of the formation of the solar system, formation of Jupiter, and showed that when Jupiter opens up the gap in the disk, its gravity will also have an impact on the inner solar system. It'll effectively create the gravitational equivalent of speed bumps, creating areas where the dust that's spiraling inwards can pile up and be stopped from traveling further in, effectively. It also creates a gap between the inner and outer solar system that nothing crosses, because if anything gets in that gap, Jupiter noms on it. And that's really interesting because some studies that have looked at primordial material we've found from in the solar system suggest that there is a bit of a chemical difference between material that formed in the inner solar system and material that formed in the outer solar system. So this gap dividing the two gives a natural way for that to happen. But the really big exciting result from this is really that modelling of the structure that Jupiter would have imposed on the inner solar system, these kind of pile-up regions where you get more dust and debris than normal, the structures that would carve out ripples in the disk effectively, and how that would then contribute to the formation of the terrestrial planets, and therefore suggesting that not only did Jupiter help the terrestrial planets form by creating sweet spots where material could pile up, but it may also have had a really strong influence on the architecture of the inner solar system by setting where the planets would form, which then would go through a bit of a randomization phase as everything collides with each other. But it kind of possibly set the blueprint for the inner solar system. And therefore, if Jupiter hadn't formed where it did and how it did, the Earth would look very, very different and we might not be here.
Yeah, it's truly fascinating. And when you look at other systems that we've discovered, exoplanet solar systems, ours is starting to look a little bit more unusual than normal.
Yes.
And Jupiter may be the reason.
It could well be. And it's one of those things. I'm reminded of the Monty Python thing. I think it's in Life of Brian, where you've got that thing of, we're all individuals. Yes, we're all individuals. No, I'm not. Every planetary system's going to be unique because it is influenced by such a wide variety of things going on. Even the stars that form in the local neighborhood, whittling it away from the outside, it all sorts going on. But what we're seeing is there's a commonality among a lot of the planetary systems that we find that look very different to ours. The thing that gives us a little bit of pause, though, is that we have these observational biases that make us more likely to find systems that are different to ours than we are to find systems like ours. Mm-hmm. And so you've always got that question of, do we look unusual because we are unusual, or do we look unusual because we're not yet very good at finding places that look like home? And that's where colleagues of mine, like Professor Rob Wittenmeyer, my colleague at UniSQ, have done really interesting work where what they do is look at what we found, but work out what doesn't exist based on what we haven't found yet. So they can start getting an estimate of how common are planetary systems like ours based on the fact we haven't found them yet. And it's a really kind of weird type of science where the absence of finding thing places limits on how common that thing is. So if you said that every star had a planet exactly like the Earth on an orbit that's 1 year long, that is exactly the same size as us and all the rest of it, then we can work out statistically based on how good our telescopes are and our techniques are, how many of those planets we would have found. And we wouldn't have found anywhere near all of them because it's really hard to do. Yeah. But we'd have found X amount. And the fact that we've only found a very small number, smaller than that, places an upper limit on how common things can be. So you get this perverse science where you get the observations that tell us what we found and what we've seen, but you can also put inferences on what isn't there and what is there based on what we haven't found yet, which allows you to put limits on how common things are that you couldn't really find very easily. Which, if that makes your head hurt, it makes my head hurt a little bit as well. But it's a really kind of clever use of the data we get to extrapolate further and draw more conclusions. And the net result of that is that the solar system is not hugely rare, but it's not common either. It's usual. And that's really cool. And that probably extends to everything. Like I say, we're all individuals. The Earth, even though it's peeing it down outside at the minute, the Earth's actually a very dry planet. If you took all the water off the Earth and made a little blob of it next to the Earth, that blob would be fairly tiny. And everybody views the Earth as being very wet, but I view it as being very dry because water is such a common compound in the universe. It's made of the first and third most common atom. You put them together, you get water's everywhere. So for the Earth to be as dry as it is telling you a lot about the uniqueness of the solar system. And maybe that's partially because of Jupiter, not necessarily shielding us from impacts, but preventing that icy material spiraling in, preventing us from becoming an ocean world. It's also partly down to the moon-forming impact. The moon-forming impact would have stripped a lot of the primordial Earth's water away because the water's light and sits near the surface. So a lot about our Earth and a lot about the solar system is down to the random nature of the events around us when we formed. The moon-forming impact, a nearby star going supernova and lacing our solar system with radioactive aluminium. Things like this, there's all these oddities that made our solar system unique. But if those hadn't happened, other things would have happened and we'd have still ended up with something unique because of other random things happening. It's all fascinating, and I just love this stuff.
Yeah, and it adds more and more weight to the theory that we are just a freak accident.
Yes.
And probably a one-off in the universe. That's one argument. So, yeah, who knows? If we find a solar system just like ours with a planet just like ours, orbiting a star just like ours, that would be the one of the greatest discoveries in astronomical history, I imagine. But so far, no.
If we do that, we would have to get in touch with the planet builders at Magrathea and demand our money back because we thought we had a limited edition.
Yes. Weren't they the white mice? Was that the white mice?
Yes.
It was. Yeah. All right. If you want to read all about it, you can find the paper, which was published in the journal Science Advances.
Roger, you're loud and clear here also.
Space Nuts.
Now, Jonti, let's move on to our next story, and this one is about a planetesimal that appears doomed, according to the paper I'm reading. It's a white dwarf that's chowing down. Very, very hungry individual is this one.
It is. So just to remind the audience, a white dwarf is the kind of little husk that's left after a star like our sun comes to the end of its life.
Yeah.
Burns all its hydrogen, becomes a red giant, and then eventually blows off its outer layers, and it leaves a big chunk of the star's mass compressed into an object about the size of the Earth. That whole process will have a fairly hefty impact on the planetary system that star's got around it. And of course, as we just discussed, we now know that pretty much every star has planets. The expectation is that when the sun reaches this stage, and fortunately it's in about 7 billion years, so nothing to worry about immediately, it will swell up and it will chow down on Mercury and chow down on Venus. They'll just be swallowed up and gone.
Yeah.
There is some debate over whether the Earth will be swallowed up or will survive just. All the models of star evolution suggest that the sun will swell up to be about the radius of the Earth's orbit. But whether the Earth is there to numb or not is still open for debate. It may be that the loss of mass from the sun in the time before may just mean that the Earth nudges far enough away to survive as a burnt husk rather than be devoured.
Still wouldn't be ideal to be around when that
wouldn't be pleasant. I mean, that said, the Earth is going to become uninhabitable a lot sooner than that because the sun's getting brighter and the Earth's oceans will boil and it'll all go downhill. But after all that process happens, when the sun sheds its outer layers, that'll have a pretty cataclysmic event on the planets and the debris that are left. So suddenly the sun goes on the ultimate kind of weight loss kick, loses mass, and that will mean that all of the objects going around the sun will be held less strongly, and so therefore their orbits will move outwards because the gravity pulling them in gets weaker. Now, if you suddenly pressed a button and vanished half of the mass of the sun, what would happen is that the speed that any of the objects are going in their orbit will be too quick for that orbit to be circular. So at that instant, at that point, they'd now be at their new perihelion, they'd be at their closest point to the sun, and they'd all move out onto much more elongated orbits with a longer orbital period, but orbits that would then cross one another. So if you imagine you lose half of the sun's mass, Jupiter moves onto an orbit where its perihelion is 5 AU from the sun, but its aphelion could be 15 AU from the sun. Saturn at the same time would have perihelion at 10 AU and aphelion at, say, 20 AU, and I'm making the numbers up a bit here. So suddenly Jupiter and Saturn are on orbits that cross one another. Their orbits will probably still have the same ratio of orbital periods, so 12 years to 29 years, but they'd scale up to be something like, 30 to 70 or something like that, because they've both moved out by the same amount. But suddenly you've got these planets that are on orbits that cross each other and therefore can really strongly interact. they can stir everything else up because all of the objects in the asteroid belt, all of the objects beyond Neptune, this happens to everything. Now, the mass loss is a bit more gradual than that in actuality. So what happens is you get the orbit spiraling out, but getting perturbed, being made more eccentric. You've also got these objects moving through the headwind of possibly half a solar mass of material being blown outwards that provides friction, and so causes them possibly to spiral inwards a bit. Causes Jupiter potentially to gather mass as it noms on all that gas that's going out. At the same time, its atmosphere is probably being blasted away by all this wind blowing past. All of this complexity means that you couldn't predict with absolute certainty what the solar system would look like at the end of this. But certainly there'd be a period of chaos. A lot of stuff would survive, but it'd survive on orbits that are now much more unstable. So you get a lot of material flung inwards, and some of that will be flung inwards far enough for it to impact on the Earth-sized object in the middle, and for the white dwarf to get a snack. Now, all that's expected to happen really early on, and over time, everything stabilizes out, things get flung around, and cleanup happens. A bit like the solar system, we were talking early on about the early stages of planet formation. Everything gets flung around, and by the time you get to now 4.5 billion years down the road, it's fairly quiet. There's a bit going on, but most of the drama's finished. So the expectation is you'd see white dwarfs that are very young, occasionally eating things, because things get flung in, and they get a bit of a snack, and the material from that snack will be spattered over the surface of the white dwarf and be visible in its spectrum as anomalous, added solid material, heavy elements. But that signal would only last a short time because the outer layer of the white dwarf is kind of a hydrogen soup, and heavier elements would sink down. So at any given time you'd eat something, the evidence for that meal would only remain for a few tens of thousands of years tops before it goes away.
Okay.
So the fact is we've seen some white dwarfs which have these anomalous heavy element readings in their atmospheres. We can tell they're eating stuff, but typically they're young. So you'd expect that. The quirky thing here is that this white dwarf, which goes by the name of LSPM, which I think is a survey name, followed by J0207 plus 3331. So that's a coordinate on the sky. So that's telling you where in the sky this is. It's a catalogue number.
Yep.
This thing is an old white dwarf. It's thought to be about 3 billion years old. So in other words, the star that formed it died 3 billion years ago. And it's been sitting there minding its own business. That's old enough that you'd expect everything to have calmed down around it. But what the new observations have shown is evidence of 13 different heavy elements, including carbon, chromium, strontium, titanium, a lot of these different elements, roughly in the kind of abundance as you'd see on the Earth, added to this white dwarf's atmosphere. So it's obviously just had a meal. And we know it's a case of just had a meal rather than it's been a leftover from a long time ago, because this stuff will sink and disappear over the next few tens of thousands of years. So what that means is that this white dwarf has just had a snack. Now, it might have had that snack 30,000 years ago, or it may still be in the process of eating as we speak. Now, what the team have been able to do is look at the amount of material you'd need to give the strength of signal you've got in the spectrum of the star. And what they've calculated is that to get this amount of material, you'd need to eat an asteroid about 200 kilometers in diameter. So that's comparable to some of the larger asteroids in the asteroid belt, but not the largest by any means. It's within the bounds of possibility of what we see here at home. But the real question is, why is it eating it now? Why is this happening now when you'd expect the system to have had plenty of time to calm down? What it suggests to me, and it suggests in the paper, it suggests in the articles about this as well, is that the only way you can get something eating this late, after 3 billion years have passed, is if you've still got a number of planet mass objects in the system stirring things up, which is what we've got in the solar system. If we look at the inner solar system, fragments of comets and asteroids are falling onto the sun all the time. We've got near-Earth asteroids, short-period comets, and long-period comets whizzing around, and they're being bounced around by the planets. Jupiter's throwing a lot of stuff our way. Their orbits are constantly getting tweaked. And so, therefore, the sun is still getting this rain of solid material falling on it as a result of the planets stirring things up. Even though the solar system is mostly quietened down, the planets are still injecting material to the inner solar system which is why we're getting meteorites, and it's why the sun occasionally gets to numb some stuff. The idea here is that this star reached the end of its life, puffed up with its outer layers. You had this really chaotic period where everything had got stirred up. Then it settled down, but because you've still got planet mass objects there, they're still bouncing around what debris is left. And we're just catching this white dwarf just at the right time when another asteroid has been flung inwards close enough to be torn apart by the star's gravity and to give it a snack. So in other words, seeing this snack happening this late in the life of this white dwarf is fairly strong evidence that planets survived the death of its star, have lived there for 3 billion years, which A, is really cool in of itself, but it also means that here is a star that we should look at when the Gaia data release comes next year, Gaia DR4, which will have been measuring this star's position on the sky. And if there are planets there, we'll be able to detect the wobble and confirm them. So it's also holding up a flag to exoplanet people saying, hey, folks, here's a target for you to look at when the data release comes out, where you might be able to find some planets, because we think there's a smoking gun here that the planets are drip feeding the white dwarf, giving it little snaps every now and again.
Okay. Wow. All right. So are there many white dwarf stars out there? What do they sort of percentage-wise inhabit the star field?
There would be a fair few of them. So the more massive a star is, the shorter its life is. And that's a really rapid function. Where that works is that if your star's more massive, its gravitational pull is stronger. So its ability to pull material into the middle of the star is higher, which means that that star's got to give off a lot more energy to balance that gravitational pull. And so stars in the main sequence part of their life are in equilibrium. The radiation coming out from their nuclear fusion in the middle balances gravity pulling in. The more massive you are, the hotter and denser you get in the middle, so the more energy you give off. And the result of that is that it varies a little bit by star's mass, but roughly the brightness of a star, the luminosity of a star, is proportional to the mass of the star to the power 4, 3.5, 4, which means if you double the mass of a star, it'll get between 10 and 16 times brighter. So twice the mass, call it a factor of 10 just to keep it easy. If it's 10 times brighter, that means it's burning its fuel 10 times quicker to produce 10 times as much energy. But it's only twice the mass, so it's only got twice as much fuel. So its life will be a factor of 5 times shorter. And the more massive you get, the shorter the life gets. Now, stars of different masses have different end fates. A star like Proxima Centauri will never swell up to become a red giant. It'll just be a dull glowing ember and eventually go out. But even the oldest stars like Proxima Centauri are still really in their youth because they're burning their fuel so slowly. Stars that are more massive eventually get stars like the sun, which are what form white dwarfs. And they eventually swell up to become a red giant, puff off their outer layers. And for a star of the sun's mass, that process from forming to the end of its life is thought to be about 12 billion years. It used to be 10 billion. Models seem to have refined, so people nowadays seem to say it's about 12 billion years. So a star of the mass of the sun that formed when our Milky Way was very young will have lived and died and become a white dwarf more than 1 billion years ago. But stars more massive than the sun can form white dwarfs as well, up to maybe 2 or even 3 times the mass of the sun, depending how effective it is at shedding mass at the end.
Yeah.
The maximum mass for white dwarf you can get to about 1.4 times the mass of the sun. If stars lose half their mass, that gives you something about 3 times the mass of the sun before you start it. 3 times the mass of the sun, 3 to the power 4 is 3 times 3 times 3 times 3. That's 81 if my mental arithmetic is correct. So 3 times the mass of the sun burns its fuel 81 times as quickly, which means it would live a 27th as long. Which means instead of 12 billion years, you get down to 1.2 billion years, you get down to like 600 million years, 500 million years. So there will have been a lot of stars that were more massive than the sun that have lived and died and created white dwarfs. And so there's going to be a lot of white dwarfs out there. I saw someone talking a while back about how old the oldest white dwarf will be and how dim it will be, because white dwarfs just cool and gradually go from being blue to white to yellow to red, gradually dim down.
Yeah.
But what that all means is that there are probably a really large population of white dwarfs out there. We know quite a large number, but we won't know anywhere near as many of them as we do stars that are actually the mass of the sun that are in the prime of their life. because they're much fainter and harder to spot, because they've got a much smaller surface area. So even though they're hot, they're tiny, and therefore they're faint. And the best example of that, of course, is the white dwarf that is a companion to Sirius. Sirius is the brightest star in the night sky. It's more massive than the sun. It's also nearby. Its white dwarf companion is something like a factor of 1,000,000 times fainter than Sirius is. So even though the white dwarf is comparable in mass to Sirius A, it is like 1,000,000 times dimmer because it's so tiny. And that's why they're hard to find.
Yeah, even though there's probably a hell of a lot of them out there. Okay. If you would like to read more about this particular white dwarf star that is, got a case of the munchies, probably spent too much time smoking the juju, you can read all about it in the Astronomical Journal. This is Space Nuts with Andrew Dunkley and Jonti Horner.
Okay, we checked all 4 systems and being with a go.
Space Nuts.
Don't know why we went down that road. Let's go to our next story, and this one is one's close to home. An object that is rapidly developing a ring system, and it's in the outer solar system.
It is. This is an object called Chiron, which was the first of the centaurs to be discovered. And I always like to talk about the centaurs because they're what I studied for my PhD. So I was, at one point, 20-odd years ago, one of the world's experts in how these things move around the solar system, and then science has moved on and I haven't. So I probably can no longer claim that. But Chiron is an interesting object. It's an icy object, a bit more than 200 kilometers across. It was one of, if not the first object to get both a classification as an asteroid and as a comet. So it was initially discovered as a tiny speck of light moving around. It's discovered by Cowell, I think, in 1970. Moving on an orbit that spends nearly all its time between the orbits of Saturn and Uranus at the minute. Long term, it's an unstable orbit. There's about a 1 in 3 chance that this will eventually end up in the inner solar system at some point in the next few million years. And that's part of the work I did during my PhD, was running simulations of where this thing's going to go. That in itself is interesting because it's about a bit more than 200 kilometers across. So if this thing got trapped in the inner solar system, it would be a comet like nothing we've seen in recorded history. Hale-Bopp, which was ridiculous, had a 50-kilometer nucleus. If this thing's 250 kilometers across, that's 5 times the radius, which means it's something like 25 times the surface area, which means it will be a lot more impressive. So it's obviously an interesting object. Back in 2011, a team of scientists traveled across the world to watch Chiron block out the light from a background star. So as this thing's moving through space, it just happened to pass in front of a star from a subset of locations across the Earth. Now, the distant stars are effectively so far away we can consider the light coming in perfectly parallel. And so a 200-kilometer centaur will cast a shadow on the Earth that's 200 kilometers across, and that shadow will whip across our planet as the object and the Earth move around the sun. The shadow moves, the Earth moves through it. And so you get a 200-kilometer roughly scale band on the Earth where that star will disappear, then reappear. We know how fast everything's moving, so if you can get in that location, have a load of telescopes spread out in a line, you can observe that occultation event, and by how long the star vanishes from different locations, you can actually figure out the shape and the size of the centaur, because you can essentially map that shadow. And if you're near the edge, the star will disappear and reappear really quickly. If you're near the middle, you'll get a longer period where it vanishes. So these kind of occultation observations are really valuable to scientists. What happened in 2011 was they set their telescopes up and started watching a bit early to make sure they were looking at the star. And they noticed the star flickered on and off a couple of times before it properly disappeared for the main occultation. Then after it reappeared, it flickered on and off again a couple of times. And that's really weird. Now, there was a kind of precedent for this with observations that were made in 1977, I believe, of Uranus, which was being observed from, I think it was the Kuiper Airborne Observatory doing one of these occultations. And they'd observed Uranus for this occultation because they wanted to understand the atmosphere of Uranus. And they figured as the star went behind Uranus, you'd see it not just disappear, but actually fade out as the light passed through the atmosphere. So you could measure the atmosphere. And with that occultation by Uranus, they got this flickering on and off thing, and that was the discovery of Uranus's ring system. So basically, the star vanished behind the rings, then reappeared, then vanished again, then reappeared, then went behind the planet.
Right.
So with this 2011 event, the same kind of thing applied. It was the discovery of a ring system around this icy object. So this is a tiny thing, smaller than even Mimas that we talked about last week with the subsurface ocean. Something so small that its gravity is probably not strong enough to make it spherical. It's probably peanut-shaped or rugby ball-shaped or something like this. It's probably not spherical. Around this object, it seems that there is a system of rings where there are 3 or 4 narrow rings at various distances. I think the distances are something like 273, 325, 438, and 1400 kilometers from the center of Chiron. Got this ring system, and it's been observed again since. They did observations in 2018, 2022, and 2023, where they again figured out that the shadow of Chiron was going to scan across the planet, got a load of telescopes, went on a road trip, and observed it happen. To get more information about the rings, because having a ring system around an object that isn't a planet is really cool.
Yeah.
And how did it form? How long has it been there? What's going on? How common are ring systems like this? Incidentally, a former PhD student of mine, Jeremy Wood, did some really cool dynamical studies that basically showed that the ring system could be primordial. It could be as old as the solar system. From the point of view of Chiron has never been close enough to one of the planets to disrupt the rings. So that doesn't put an age limit on it, but it was still quite cool. What the new observations have shown, though, is that the ring system now seems to be different to how it was in 2011. In other words, the ring system is evolving before our very eyes, and it actually seems to be a denser, stronger ring system now than it was 10 or 15 years ago. So it's possible that we're actually witnessing this ring system as it is forming or as it's changing over time. Now, I know Chiron has been quite active. It's been outgassing because it's been closer to the sun, hence the cometary type classification it got. Maybe some of the material it's ejecting in that outgassing is being ejected gently enough that it doesn't escape from Chiron, and that's repopulating the rings. We just don't know. But the only way we'll find out is by doing more of these observations. But I think it's just really exciting, and it's a really good reminder again that we always kind of imagine the solar system as a very staid and boring, placid place where not much is changing anymore. Because it's 4.5 billion years old, and as you get older, you get a bit more sedentary and not much happens. But in fact, it's a reminder that the solar system's a really dynamic place and things are constantly in flux, constantly changing. We talked about it last week, the ocean on Mimas, that is possibly only 15 million years old. Now, 15 million years sounds like a really long time. But in a system that's 4,500 million years old, that's like something that has happened to me in the last couple of weeks. That's a new feature, not something I've had since birth. And this is yet another example of the fact that the solar system just seems to be continually rapidly changing and evolving.
Yeah, it's a really interesting situation. How far out is Chiron?
It varies. So at its closest to the sun, it's a little bit closer to the sun than the orbit of Saturn. At its furthest, it's a bit further away than the orbit of Uranus. And that's an unstable orbit, so it bounces around over time. It will have encounters with them that fling it around. But at the minute, it's in the outer solar system between the orbits of Saturn and Uranus most of the time. Unstable solution. It probably originated out beyond the orbit of Neptune, and it's one of this population called the Centaurs that are the future parents of the next generation of short-period comets, effectively. In the same way that the near-Earth asteroids have their origin in the asteroid belt, short-period comets have their origin in the trans-Neptunian region. But to get here from there, they've got to pass through the outer solar system, and that's what the Centaurs are.
Okay. Fascinating. Yeah, it's really interesting and probably not one that too many people would be aware of. I remember when it was making the news some years ago, and that's why the name stuck when you sent the story to me. But you don't really hear much about it. But now we've got a very good reason to look at it. If you would like to look into that particular paper, it's been published in the Astrophysical Journal Letters.
0G, and I feel fine.
Space nuts.
Our final story, Jonti, is an exoplanet that the popular press are going to say has got some kind of life on it. It's a maybe life candidate. story, this one. And but they're still using the term super Earth.
Yeah, I'll keep this one a little bit short and try not to get too grumpy. But one of my big bugbears all the way through my career is a good way for people to get media coverage of their new planet discovery is say, it could be habitable. It's in the Goldilocks zone. Hooray.
Using the L word.
Rumble, rumble, grumble, grumble.
It's a 4-letter word too, that one.
It is. And it's one of the terrible 4-letter words. Part of the problem here is there's this concept of the Goldilocks zone and the habitable zone, which has become really entrenched in the popular consciousness. And it's always viewed as being this sweet spot for life. And the idea is that if you have a planet in the habitable zone, it will have liquid water on its surface and all sorts of happy life things will happen and everything will be good. What it actually means is that if you took the Earth as it is today and put it where that planet is, the Earth would still maintain its liquid water. Because planets are really diverse. If you took Venus and put Venus where the Earth is, with Venus's current atmosphere, Venus would be too hot to have liquid water. But if you observe the solar system from a long, long way away, and you discovered Venus on the Earth's orbit, it wouldn't look any different to the Earth. It's a planet about the size of the Earth, sat in the habitable zone. It's habitable, hooray. Whereas Venus is actually so hot that on the surface it'd melt lead. And I certainly wouldn't want to visit there. It's even hotter than my room was the other night when the power cut had happened. And that was bad enough and brutal enough. So what this means is that people have become very fond of find a planet around a star. You can work out where the boundaries of the habitable zone will be based on a few assumptions. And this is work going back about a decade of the definitions we use now. And you've got the conservative and the optimistic habitable zone, which are basically loosely based around the fact that if you're as close to the star that you get an amount of radiation coming in comparable to Venus, you'll be too hot. If you're about where Mars is, you'll be too cold, but in the middle, you'll be just right. And that's about it. Now, that definition doesn't really take any account of the mass of the planet or its atmosphere. What that means is that when you find a planet that is a super Earth, that is 4 times the mass of the Earth, that is almost certainly nothing like our planet at all, you'll do a calculation and say it sits in the optimistic habitable zone, so there is a potential it could have liquid water on its surface. That's full of a whole heap of assumptions, but to me, it's a really long stretch from saying it could have life. A, you're assuming it's got the right kind of atmosphere to have liquid water, where it's 4 times the mass of the Earth, so its atmosphere is almost certainly much, much thicker. Therefore, likely has a much stronger greenhouse effect. Therefore, probably runaway greenhouse, not good. The other thing with this particular planet, GJ251c, it's a super Earth orbiting a red dwarf star. Nearby, less than 20 light years away, and that's part of why people are excited, because it's near enough that we'll learn a lot more about it in the future. However, planet orbiting a red dwarf star means that to be in the habitable zone, it's got to be close in. This thing goes around its star every 54 days, which means that it is closer to its star than Mercury is to the Sun. And given the difference in their masses, it's actually much closer in than that. That means it's up close and personal with a red dwarf star, which are notorious for being active and flary and noisy, particularly when they're young. They're tempestuous teenagers in their early days, with mega stellar flares and stuff like this. So it seems to be fairly widely accepted that planets around red dwarf stars that are close enough to be warm enough to have liquid water will have a hard time holding onto their atmospheres, particularly when the star's young, because it'll be having all sorts of bonkers fun. And that's kind of borne out with the planets around TRAPPIST-1, which for years have been people saying, these are the most Earth-like planets ever, and we'll find life on them, and hooray. And then when they finally got to use the James Webb Space Telescope and look at those planets, none of them have an atmosphere.
Yeah.
Now, I don't know about you, but I kind of like to breathe. It's a fairly important part of living, and a planet without an atmosphere is not going to have liquid water on the surface, because if you take the atmosphere away, there's no pressure, the oceans boil. And then are blown away by the red dwarf star, which makes that planet a desiccated husk, which is not particularly habitable. The reason I get energized and activated about this, it's a lovely discovery. It's a really interesting planet. We'll learn a lot more about planets elsewhere. If there is an atmosphere, it's around a star that's near enough to us that with James Webb we'll be able to study it, learn more about the atmosphere. We'll learn a whole heap from it. But I get really energized about this because there's only so many times that people can hear a story that says, we found the most Earth-like planet ever. before they think we found the Earth, before they think we found life elsewhere. And that then really devalues it when we finally do find planets that are properly like the Earth. When we do find signs of life elsewhere, scientists will be getting really excited because we've finally done it, and everybody will be like, well, why bother? You've done this a million times before. The whole boy who cried wolf thing.
Yeah.
And it, again, a big bugbear, and something that's really critically important these days is trust in science and trust in scientists. We've got all the controversies about topics that are much more controversial than we're talking about with astronomy, with vaccine denial, with climate change denial, with people refusing to evacuate in the path of a hurricane that's coming because they don't believe the scientists.
Yeah.
Anything that makes people less trusting of scientists because they're overblowing stories is damaging now far more than it has been in decades past. It's part of why I get so frustrated with Avi Loeb and 3i Atlas. It's why I get frustrated with the media coverage of stories like this and the scientists pushing, I think, somewhat unethically, an argument that this could be a habitable planet, because it makes the rest of us look like fools, and it makes people, it gives them ammunition to say, well, scientists lie to us, when they're not. They're saying that this meets the criteria for the habitable zone paper that was published 10 years ago. But it weakens that trust in science, which is so important now more than it ever has done. And I said I wouldn't go on a rant, and I'm now waving the flag and banging the table and all the rest of it. But it's a frustration that's wider than this story. And this story's lovely. It's an awesome discovery. They found a planet going around a star that's very cool. We'll learn a lot more about it. It's a brilliant result. You don't need to tag every result like this and say that this planet could have life.
And yet that's what happens. It's sort of like what artificial intelligence is doing to social media. You don't know what you're looking at anymore. And my trust levels have dropped significantly in recent months.
Well, my dad would say that. My dad is 80 and he's still on Facebook and he doesn't like it, but he's on it because it's a way to communicate with people back in the UK. He moved over here a few years ago.
Yeah.
And he's constantly saying to me he's getting so frustrated with these AI stories and fake news things that he doesn't know what to trust on there anymore. Because he'll see a story that some famous actors died, and then he'll look up on Wikipedia and they're still alive and kicking and they've got a film coming out. But there's this thing of you'd never believe the tragic photos. And it's bizarre. And at a time when we need fidelity and trust in our news and trust in our science, we've got to be careful about how much hyperbole we put into stories, I think.
I totally agree, yes. If you'd like to read about that particular exoplanet, you can pick up that yarn through the Astronomical Journal where they publish the paper, or you can read up on all the stories we've talked about today at space.com. And I'm sure a few other platforms have published them as well. And that brings us to the end of this program. Jonti, thank you so much.
That's a pleasure. It's lovely to chat. Thanks for bearing with me being a bit flighty and floaty thanks to the power cuts and the weather.
You've done well. You've done well. We'll catch you on the next program, a Q&A program. Jonti Horn, a professor of astrophysics at the University of Southern Queensland. And thanks to Hugh in the studio who couldn't be with us today because he never tells me. I have no idea. I just make up the reasons he's not here. I honestly don't know why he didn't turn up this week. Probably because we didn't tell him when we were recording. Yeah, that might have been it. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.